Coming up, the latest quantum news on Amazon bracket, and later in this video, Rivelane, from McDade, Quantum Network. We are currently in our subscriber building phase, we need your help. Please take a moment to subscribe to the channel, just like Schrödinger's cat, so that we can continue to provide you with the latest news on quantum computing. Thank you. Amazon bracket, a service for exploring and evaluating quantum computing. Amazon bracket is a fully managed service that makes it easy for scientists, researchers, and developers to build, test, and run quantum computing algorithms. Amazon bracket helps you get started learning about quantum computing by providing a development environment to build quantum algorithms, test them on simulated quantum computers, and run them on your choice of different quantum hardware technologies. Amazon bracket lets you design your own quantum algorithms from scratch or choose from a set of pre-built algorithms. Once you define your algorithm, Amazon bracket provides a fully managed simulation service to help troubleshoot and verify your implementation. When you are ready, you can run your algorithm on your choice of different quantum computers from their quantum hardware providers, including D-Wave, IonQ, and Rigetti, all accessed through a single user experience. To make it easier to develop hybrid algorithms that combine classical and quantum tasks, Amazon bracket helps manage classical compute resources and establish low-latency connections to the quantum hardware. With Amazon bracket you can explore quantum computing, evaluate its potential, and build expertise for the future. Coming up next, Rivelane. We will be back after this brief message. And now, Rivelane builds groundbreaking software to unleash the power of quantum computers. Rivelane builds transformational quantum software. Their software transforms quantum computers from experimental technology into commercial products. They tease the highest possible performance out of quantum software to reach quantum advantage sooner. By making Rivelane software portable across technologies, early adopters don't need to choose which technology to pursue. Solving the problems that matter. Rivelane goes deep into the stack so that their hardware partners can focus on the physics and build better full-stack solutions. They work with the chemical, pharmaceutical, and materials industries to improve algorithms and specify early killer applications of quantum computers. Rivelane's vision: to develop pioneering quantum software that gets its customers to quantum advantage sooner and unleashes the power of quantum computers. Rivelane's mission: to build an ultra-low latency quantum operating system that accelerates quantum classical hybrid algorithms and facilitates hardware R&D, and to develop algorithms making optimal use of the full quantum computing stack. Rivelane's call to rethink quantum computers. The constant breathing of the dilution refrigerator as it pumps helium-3 around the system is the only thing you hear in a lab with a superconducting quantum computer. Every 10 nanoseconds a pulse is triggered from an FPGA, a programmable piece of hardware, that causes the next signal to be sent into the fridge. Other signals spark measurements of the quantum system buried deep inside. All of this happens with exquisite timing as the entire operation lasts less than a single millisecond. Quantum computers are much more than just qubits, they are a complex control system with different computing elements, from analog hardware to FPGAs and CPUs. These elements keep the qubits alive. Rivelane knows that if they want to build great quantum computers, they need the infrastructure to manage the stack, by starting deep down in the control stack and building up. Early in the development of traditional computers, von Neumann proposed a new model of a computer. One of its first realizations, the EDSAC, was built here in Cambridge by Maurice Wilkes. It was so successful that it was mentioned in 3 Nobel Prize speeches. In this architecture, the elements that store information are distinct from those that process information. Programs and data are stored in memory in the same fashion that enabled reprogramming and automated programming tools. This allowed engineers to build assembly languages and compilers, then high-level languages like Fortran and, today, Easy-to-use languages like Python, with libraries and software as a service tools that have accelerated the pace of the software industry. The stack was built from the bottom up. The quantum stack is being built upside down. We have qubits and, since we know how to design great languages, many high-level development kits. All of those are based on the circuit model, a CPU directly controlling a QPU, which was popularized in the 1990s in the classic textbook by Nielsen and Chuang. This model disregards what actually goes on in the heterogeneous control stack. It presents quantum computers as black boxes in which only the bottom and the top layers are of relevance. All the middle layers are hidden away. As programmers, we want to use every bit of resource that we have, and that means every bit of coherence time. We want to write programs with the capability to react fast to what's happening down at the qubit level. This is especially true in the NISQ era, in which quantum classical hybrid algorithms are, hopefully, going to carry us to quantum advantage. To achieve that, all layers of quantum and classical compute will need to be integrated as tightly as possible. This includes the middle layers. These middle layers of the quantum stack currently consist of fast programmable logic, FPGAs, and non-programmable logic, the waveform generators, digitizers, etc. FPGAs allow for fast feedback and flexibility whilst we refine the next generation of quantum hardware. Eventually, they will likely get replaced by custom hardware with a fixed function, for example, error correction, but that custom hardware can't get built without the software layer providing the infrastructure. Lowering latency in the quantum system also allows for system testing between program runs, which means you can run more tune-up experiments, such as randomized benchmarking. All of this is essential to reduce the cost and time to build a truly groundbreaking computer that will undoubtedly be mentioned in future Nobel Prize speeches. With that thought in mind, Rivelane needs to develop a better model of computing, similar to the von Neumann model, and build the stack from the bottom up. This is what will make quantum software thrive. It will allow quantum hardware developers to focus on the physics and build the next generation QPUs. This is their mission at Rivelane. They are proud to be working with some of the best hardware labs in the world. Support the channel with a $50, $25, or $5 donation, or any other amount you choose. Your donations are greatly appreciated and allows McDade Quantum Network to continue to produce great news and content on the major players in quantum computing.